Welcome the first of our speakers to kick us off, Patrick Mills from Texas A&M University. And I see you've already started sharing your screen, Patrick, so we're good to go. Please go ahead.
Hey, okay, thank you. Thank you for the intro. And wish to extend my greetings to everybody that's joined the session today from South Texas, where it snows maybe here, maybe once every 30 years, simply by accident. So today what I wish to do then is to talk a little bit about, give a quick overview about how Maple is a useful tool for analyzing models and data that are obtained from tracer testing. So the idea behind like a tracer test is sort of illustrated here, actually in a title slide. So you have a system that may either be a batch or it can be a like continuous flow system. And what one does is you introduce, as you can see here on the right-hand side, some type of like disturbance in the inlet. And then you measure the corresponding output response. And from that information, you try to infer what's happening in that particular system. Now, the system can be anything really. It can be a human body, an animal body. It can be a process system, anything that you're able to introduce some type of device or some type of method of, say, perturbing it. In terms of the background of tracer methods, this is basically summarized here. It really goes back more than 100 years, where George de Hevesy, he was a Hungarian radiochemist. He made an attempt to separate radioactive lead from stable lead back in like 1911. About 10 to 12 years later, he was able to quantify a dose-dependent lead uptake in plants. And that work he did there really was the starting of the field of like nuclear medicine, which is, of course, a very critical aspect in like medical technology. For his work, he actually obtained a Nobel Prize in 1943. And what happened is that scientists and engineers basically saw that approach and said, well, let's try to use this same approach to quantify flow and transport. And we'll do that not only using reacting type of molecules, but we also can use inert systems. Some examples where tracers have been used are listed here in the bullet points on the on the left. And off on the right side over here, you see some like notable figures in science. Of course, Osborne Reynolds, whose classic dye experiments led to the concepts of laminar and like turbulent flow. In like the 1950s, a gentleman in England, like P.V. Danckwerts, he really developed the whole theory of like RTDs and defined some of the basic probability density functions that are used in like tracer methods. Later on in the 50s and 60s, Taylor, he actually was able to quantify how like dispersion occurs in like laminar flow and how that relates back to the response of a system. So we use tracer methods to determine basically system behavior. Anything that has a flow, or even it can be a batch system, as I mentioned in the starting comments. And we may want to understand what happens there, and we use that with some type of tracer. So in early engineering practice, when I say early, this is maybe before the 1950s, people that like designed systems either assumed ideal plug flow, as illustrated here, or ideal mixed flow. Of course, in like plug flow, the fluid flows down the conduit. There's no forward or back to diffusion of that flow. Flat velocity profile. The other extreme, of course, is mixed flow, where the concentration in the mixing zone is everywhere the same. So the exit composition is equal to whatever composition exists in the system at that particular time. So basically, the method was adopted then as to give an idea of how actual systems operate. And here we see some examples of ideal versus non-ideal behavior. If you were introduced a tracer here in the inlet of the plug flow reactor, at some time later, you would see a perfect Dirac delta function. But as different different effects occur in the system, you can basically get a spreading of that signal, if you will. And this illustrates the X-age distribution for a partially backmixed system, and in the case of complete backmixing, the X-age distribution is an exponential function. Now, without even doing a model and you do an experiment, you can then detect things like stagnancy. You see here the tracer comes out, but then there's a long tail. You can detect, of course, bypassing effects. So you introduce the fluid here and it doesn't get completely mixed, but it ends up going out the exit. You would get some response that looks like this. On the hand, if the effluent was being, say, like recycled, then that concentration would then be seen, and you would get a decay was superimposed with these peaks that you see over here. So in actual systems that's used as illustrated over here, you could use this to detect all types of effects. Now, as I mentioned earlier, P.V. Danckwerts, he laid the foundation for different types of age distribution functions, and we can see what those are. We have the X-age distribution, quantifies the fluid with ages between T and dt, and an illustration of that is shown here on the figure up there on the upper left. We have the cumulative age distribution. That's the fraction of fluid outflow with a residence time less than T, and that's often done by introducing some type of step function. The other opposite of that was what we call the washout function. This would occur if you would turn the step function off and then allow the tracer, as it implies, to wash out. So these are the basic fundamental functions. Of course, others can be also defined as well, and those give other types of information. This can be applied to like a two-phase system as well. So you may have a gas liquid flow or some type of multi-phase flow. And you can introduce a tracer, and it then may mix and disperse itself between the two phases, giving you two responses, the analysis of which can be used to interpret what's going on. All right, so what we're going to use in the models that we're going to look at here for tracers, we're going to use the Cayley-Hamilton and also the Sylvester theorem, which you all know, I'm sure. So let's get right to it. So here's an example where we have continuous flow stirred tanks in series. So we have a series of tanks in which we introduce some type of disturbance, and we assume that this system is undergoing, the tracer can undergo a reaction. We could turn the reaction off by basically setting the rate constant equal to 0, in which case we would then have the response of a sequence of vessels, continuous vessels in series. So we use Maple to describe this. We basically wrote a code that implements the Sylvester and Hamilton-Cayley theorems. So we could write that system of equations for arbitrary number of tanks in those chemistries as in this matrix form, and we could look at the response of that and how those systems behave to a step input, as you can see over here in the lower right. Now, if we turn the chemistry off, then we then can look at the responses to a step, and of course the derivative of this is the X-age distribution. So once one obtains the expression for the step, the derivative can be obtained, and from that you get the pulse response. And you see, of course, as the number of tanks increases, it goes from a ideal stirred vessel to a one which is non-ideal, and it actually, in the limit as n goes off to infinity, this would be ideal plug flow. So this type of model is very useful for capturing the behavior of systems that vary anywhere from ideal plug flow to points to basically perfectly mixed flow. Another useful problem is maybe you want mixing that occurs in between the two, so you can introduce recycle. And there's many applications of this, and for example, in the field of reactive mixing. And so here's an example of a model that one can construct and set up in Maple to contain the corresponding responses. Of course, we can add any number of vessels to basically alter the distribution. So over here, we see what the Maple model tells us. Turns out that earlier, another work was done to develop that. They actually led to a Voltaire integral equation. But we could set the Maple model in using the tools in Maple to predict how the system will respond over different levels of recycle. Now, we also can apply this to, here's a very good example that occurs in practice. we may have a fractionation column or any type of stage device that has countercurrent flow, as illustrated over here. And of course, one can write this in a matrix form, as shown here, and then using the Hamilton-Cayley theorem and the Sylvester formula, one can then determine the solution, the transient response of the system to a step input. And so you can get the responses in. We have a code that will do that for any number of stages. And this is very useful in practice because then one can then use this to diagnose the behavior of state systems. Another area we looked at is how Maple can be used to develop models for biomedical systems. And here's an example of a compartment model. We won't go into the details of this, but basically, this is used when you have a positron, of course, like emitter tomography, PET. So what we do is this thing is used to quantify as it indicates here, the rate of cellular behavior. And that's typically maybe in a person that may have cancer, for example, and they use this then to obtain information about the rate of growth, basically. Now, so there's a differential equation model here, and then of course from those responses obtained from the PET, you can then identify the various kinetic parameters, and that's very useful for larger scale models where this may be a subset of something. Okay, so we did a little whirlwind tour here, but basically the tracer method is very useful for characterizing non-ideal systems, either batch or continuous, and it can be applied to a wide range of systems across science and technology. In order to do it, one has to integrate, of course, modeling, mathematics, computational sciences, and of course, things like chemistry, physics, biology, and so forth in order to develop such models. Well, now, what we noted, we think the platform, of course, is very strong platform, obviously, but it doesn't seem to be very widely used, okay, in this area. So there's very limited examples we found where their tracer methods have been used. We, of course, teach this here, but we also perform, of course, research in this area, and we're thinking that maybe some kind of package or some kind of platform as an add-on to Maple would be very useful. There's a list of references. My plan is to write this up and to submit it to the Maple Journal and give a lot other details which I didn't have time to talk about, of course, here like today. Okay, so I'd like to thank you then for your attention, and we'll be glad to answer any questions or make any comments.
Thank you, Patrick. If their audience has any questions and wants to go off mute to ask, go ahead at this time. Okay. Otherwise, I had one quick question myself. So
Yes.
I noticed you're using transforms for the tracer function. What about cases where no exact form of the transform can be obtained?
Yeah. So yes, that's a very good question. Yeah, typically, if we have a linear system, of course, we could try to use, of course, Laplace transforms
Yes.
to do that, and we've done that many times. What we found is that when we get to more complex systems, trying to find the inverse can be a very challenging problem.
Very challenging, yeah.
Very challenging. And so you, of course, may end up using the residue theorem and so forth, but you still may have a little issue. Now, the couple things you could do is that you could find the moments of the distribution obtained from the various derivatives of the Laplace transform, and the moments are very useful because they give you an explicit formula that relates back to the model parameters. So the moments, which can then be derived from the actual data, provide a way of getting initial estimates of those particular parameters. Of course, the other way is to do a Laplace transform, of course, inversion with the numerical tools there.
Right. Yeah.
Okay, and so there's a couple of other approaches that can be used. What we try to do, we try to get a direct time domain solution if we can. Okay, if we cannot, then we can resort then to other approaches to do that.
Okay. Excellent. Thank you.
Okay.
Any other questions?
And not at this time, no.
Okay, perfect. We'll move on to our next speaker. We're going to shuffle the order a little bit. Rosario, if we could get you to go next.
Okay, I share the.
Perfect. So our next speaker is Rosario Rubio from Universidad Nebrija. Did I pronounce that correctly? Nebrija?
Yeah, Nebrija.
Okay, perfect. And yes, we can see your screen, so please go ahead.
Okay. Oh. Perfect. Let's see. Okay. Hi, everybody. It's great to be here with you. My name is Rosario Rubio, and I'm glad to be part of this session and to share this work together with Tomás Recio and Pilar Vélez from Nebrija University. The title of our talk is Addressing with the Concourse of Maple, Diverse Open Issues Dealing with the Manifold and Subject Concept of Geometric Locus. In the next few minutes, I'll give you a brief overview illustrated with some examples of what we have been working on. Locus computation is a key topic in dynamic geometry. In fact, Maple Transactions has published 3 articles in this subject in the last 3 years, which shows the growing interest of symbolic approaches to geometry loci. Locus computation has long been considered a defining feature of dynamic geometry software. As Gao stated in 1999, it is one of the 5 basic properties of digit systems. Even early systems like Sketchpad include locus-related functionalities over 60 years ago. Despite its importance, current digit programs often fall short. They typically offer either visual plots or numerical approximations. Symbolic locus computation is still missing even in systems like GeoGebra that integrate computer algebra. Let me show you 3 examples illustrating this gap. In the first one, we ask GeoGebra Classic with AuGeo Online for the locus of a point C such that the segment AC is twice the segment BC. The output is the red line, the red curve with approximate equation described in this left column. The curve appears to be a cycle, but what is the center or its radius? In what sense does it depends on the initial points A and B? On the other hand, this object cannot use as an input of automatic proof. We cannot verify if we place a point P in the locus satisfies that the distance of PA is twice PB, or see the proof with show proof. So we can. So we just can hypothesize or use another tools for this part. Sorry. Again, with AuGeo line, we show another basic geometry locus. Here, C lies in the perpendicular or AB, and we want to find where to place the point C such that twice the legs are equal the square of the hypotenuse. There is no graphical output, and the numerical output is a 4-degree equation. If we translate this example with GeoGebra Discovery 5, which is the computer version of the GeoGebra Discovery program, we visualize the geometric location, these 2 points, but again, we don't know what relationship do they have with the initial data A and B. Our final goal is to implement a symbolic algorithmic approach to locus computation in GeoGebra Discovery. This would allow for automatic verification and interpretation of results. To achieve this, we are experimenting with Maple to explore different algorithmic possibilities. This leads us to several symbolic computation challenges. For instance, how should we treat parameters? Are they variables or constant? Should we eliminate over the coordinates of the locus point or over the entire constructions? Should we specialize first or compute the generic locus first? For the first three questions about the role of independent variables or parameters have been partially addressed and published in Maple transactions. The role of Maple to verify conjecture has been crucial. Here we pose two results. The first lemma, we consider P the set of independent variables, Y the set of locus points coordinates, and X are the extra variables. And states that the more reasonable protocol, but not implemented yet in DG software, could be to treat parameters as number. So to eliminate the standard construction ideal C over, over the field KP. Such elimination involves fewer variables as the P variables are treated as constant. However, finding elimination algorithms that work over a field that's such KP is challenging. Therefore, the more reasonable protocol to deal with this issue is to prefer elimination with the polynomial ring KPXY over KPY. The lemma asserts that the generators of this elimination are also valid as locus equations under the other approach. But if we want to profit from eliminating from over the field KP, since this has less variables, we can also use the second lemma that declares that it also works assuming that the hypothesis ideal has no components involving parameters. But this is a work in progress. For the last question, related to discover geometry statement by looking for the locus of some point in a construction that verifies central constraint, given a construction with hypothesis H, in this example, in this example, the points A, B, and C, and a locus constrains the locus of C, we get the output, the red curve. In this case, the locus is a consequence. Thus, a necessary condition of AB to be twice BC, which implies that C is in the red curve, but we want to discover. If that means if C is in the curve, that implies that AC is twice AB. That is, CB in the cycle is a sufficient condition. This happens many times. Necessary becomes sufficient, but not always. Not always this is true. This is a work in progress on automatic derivation in a statement. And it seems that asking for a locus automatically discovers some theorems. In fact, this is sorry. Sorry. Well, now we need to use Maple in order to get more further. Now we saw an example how Maple helps addressing such issues. This example comes from a group of fans of elementary geometry statement with Facebook, blogs, Telegram address, etc. The answer in GeoGebra discovery is a cubic equation, this red curve, but we cannot prove formally with GeoGebra discovery that placing a point F in the curve, the three black lines here are concurrent for several reasons. The output, the qubit equation, is numerical depending on A, B, C and PP. For computing the generic locus, we need Maple. Even if we could guess the property of the qubit, we don't know how to construct such a qubit with GeoGebra discovery tools. Moreover, even if we could make such construction, placing a point in the cube and checking the proof of the statement could be perhaps very hard computationally speaking. So maybe Maple is absolutely required to analyze this problem. Next slide provides an example of how we deal with this topic with Maple. Without loss of generality, we assume in this example that A is in the origin, that B is the point 1, 0, and that C is not aligned in AB. The steps of in the construction generate the ideal called PP. This ideal has dimension 6 with C, F, and P as free variables. So the locus F verifies that the three black lines are concurrent. Now we add the collinearity condition of the lines to the hypothesis ideal. This new ideal has dimension 5 with C, F, and P1 as free variables. Next, we eliminate C, F, and P, and we get a cubic curve in coordinates of F, and we consider C and P as coefficients. It's easy to prove several properties with this curve. For instance, in the first one, we show that the point A is in the curve, and here that the point B is in the cubic. And to display the cubic, we will some values to C and P. Look that it is similar the one that GeoGebra discovery displayed. And here we did first specializing and then eliminating, as GeoGebra discovery does. But notice if we first eliminate and then specialize, we get a multiple of first specialize and then eliminate. But both curves are of degree 3, so they coincide.
12-minute warning.
Okay, now we consider the ideal H8, which is the thesis with the hypothesis P plus the cubic. This ideal has dimension 5 with, and by human intuition, we consider C, P, and F1 as free variables, based that there is an equation involving C, F, and PP. And with the negation of the thesis, we get it's not 0. That means that it's generally true. It's true except for some degenerated cases. We can analyze these degenerated cases by factoring the results. For instance, here we get that F is aligned, that it is true except when F is aligned in AB, or for instance, P aligned with AB. And so except for this last result that we could not interpret what does it means. So as can be seen in this example, the concourse of Maple is very important to try to address the issues we have raised before, to improve and adapt locus computation with GeoGebra discovery to educational context. But it is still a work in progress. So that's all, and thank you for listening.
Thank you, Rosario. Does anybody have a quick question? We've still got a minute. Alex, did you have one?
Someone just sent one over to me. Hi there, Rosario. Thank you very much for your time. Have your team noticed any ways to improve computational efficiency of the geometric evaluation? So when you're doing the Maple work.
We have come across with several with several examples, and some are the conditions are different from the others. So we don't have a general condition for everything. So we need to get across with more work.
Okay.
Thank you. Yes, and
Excellent.
certainly seeing
Thank
the
you.
progress year to year is really good. Thank you for sharing.
Thank you.
Excellent. Thank you. And so I'd like to move on and to our next speaker, Laureano Gonzalez Vega from CUNEF Universidad. Laureano, are you, if you could start sharing screen, please.
I'm here. I will share my screen.
Perfect.
Okay, let me 1 minute. Do you see my screen?
Yes, we all see it fine. Thank you.
Thank you very much. So thank you very much for the presentation, Alan. Let me start with the reason why we are interested about this closed formula for the relative position of two conics. The key point is that we are interested about some problems involved in robotics or computer animations where the objects to deal with are represented or in some sense enclosed by conics or quadrics. And typically these objects are moving, and the key point is just to detect when these objects, they do not collide. And so this is the reason why we are interested about this formulae for detecting in advance what is the geometric configuration of the two considered conics, but this is very important without computing the intersection points. So this is something that I want to put clear enough at this moment. So the problem we are dealing with is that, in some sense, simplifying, we have two conics given by these two quadratic equations. The a's and the b's are the coefficients, and in some sense are for us parameters. And we want to have a formula involving only the coefficients, these parameters, in order these two conics, for example, two ellipses, they are clearly separated, so they don't have a common interior point. No, this G of the A's and the B's are the formula we are looking for. Fortunately for us, coming from real algebra geometry, there is a technique involving solving this kind of problems. For example, the most typical example is looking for the conditions B and C, real numbers, must verify in order this quadratic equation has a real solution, at least one real solution, and this formula is equivalent to the condition b squared minus 4 times c bigger than or equal to 0. So what we are looking for is an equivalent formula, but for these more complicated situations. Two quadratic equations in x and y, and we are looking for the conditions in the coefficients in order these two, for example, ellipses, they do not share any common interior point, or in some sense, we say that they are separated by a line. No? Fortunately, using quantitative elimination, this formula exists, but this is very complicated. There are algorithms producing for any formula involving quantifiers, the equivalent formula without quantifiers involving only, in our case, the coefficients of the two conics, but these algorithms are very far from applicable in practice. But for very concrete problems like the one we are considering, we are able to deal, in some sense, this is what I want to show today with this problem. No? So summarizing, like our motivation, what we are looking for are for this simplest formula, in the sense that we are getting not too much polynomial conditions, inequalities, and not too complicated equations involving the coefficients. We do not want to compute at all the intersection points. So just we want a formula that once the formula is verified, what we know is that this is the geometric configuration corresponding to what we're looking for. So after this motivation, let me give you what is happening, for example, for the case of two ellipses. For two ellipses, the key point is just starting with the seminal paper of Wen Ping Wang and his collaborators, and I will illustrate this starting point by the case of looking for the formula for the two ellipses, the two considered ellipses, when they are separated by the line, and they do not share any common interior point. No? If this is the equation of our conic, of our ellipse, we know that we can represent this equation by the corresponding symmetric matrices. And if we have two ellipses, for example, A and B, the most important object that we are going to use today is just what is called the characteristic polynomial of the pencil defined by A and B, which is the determinant of this matrix, lambda times A plus B, which in this case is a cubic polynomial where the coefficients A, B, C, and D are polynomials in the coefficients of the two matrices A and B representing the two conics. I was mentioning that the starting point for this approach is the paper or the work by Wenping Wang and his collaborators. And for example, if you look to these third conditions, this third condition is saying that the two ellipses we are considering are separated by a line. This means that they do not share any common interior point if and only if these cubic equations, universal equations, has exactly two different positive real roots. In fact, in this case, also the other root is negative. So we are moving a geometric condition to a condition about the signs of the real roots of this cubic polynomial, and determining conditions for a polynomial, in this case, a cubic polynomial, in such a way the real roots have some fixed sign behavior. This is something that quantifier elimination is able to produce or to compute in an easy way, no? So a natural question in this setting is if the sign of the real roots of the characteristic equations for A and B are enough just for considering or for characterizing all possible geometric configuration. And the answer is no. For example, if you look to this table, you can see that if the three real roots are negative, we have 4 intersection points, the first possibility, but also this corresponds to the case where we have that these are the 3 negative, this is the same time here, both conditions are the same, but the geometric configuration is completely different. So in this case, to separate all possible configurations for two ellipses, we need to add what we call the nature of the degenerate conics in the pencil. In the first case, for example, this means that in this case, for alpha, for beta, or for lambda, when introducing the pencil, A plus lambda times B, in this case, we have 3 pairs of real lines, which is different what is happening here, that we get 2 pairs of real lines and 2 pairs of imaginary lines. But this was enough to solve this problem. In 2006, we were able to produce what we are looking for. The two ellipses are separated if only if these two conditions here, these 4 sign polynomial equations or these 3 sign polynomial equations are verified. Do not forget that in this case, A, B, and C are rational functions in terms of the entries of A and B, the matrix A and B, that's what we are looking for. This was simplified and improved later, getting that these conditions here can be are equivalent to those here. And at the end, we get for this case something what we are looking for, which is this kind of a scheme where we know what is the conditions, in this case, separate overlap of external tangency, just involving polynomials in the coefficients of the two considered matrices. Here, bar means the number of sign conditions into this set of 4 numbers. This is negative and this is negative. So let me mention before entering in the next step is that this kind of formula have a lot of applications in soft matter, computational physics, optics, and have been used at least in these concrete references. So moving to the general case, let me move to the case of two ellipses was solved completely. For each geometric configuration, we have a concrete formula characterizing this configuration. And what we are doing now is just moving to a more general case, the case, for example, of one ellipse together with a parabola or hyperbola. And both cases follows in the same way. The first step, we consider circles and parabola and hyperbola in canonical form, and we characterize all possible geometric configurations in terms of the roots of the characteristic equation and other parameters, involving typically the parameters defining the parabola or the hyperbola when in canonical form. Second step is when quantifier elimination appears, and we move the conditions on the roots of the characteristic equations to conditions on the coefficients of the characteristic equations. And the final step is just inverting this transformation, moving the circle to the ellipses and moving the parabola and the hyperbola, not in the standard form to the general form. And here Maple is crucial. So Starting with the case of a parabola and an ellipse, first step, we consider the parabola in canonical form. Well, in this case, we can consider also the circle in standard form, but in this case, the center are not in the origin, in this case. First step is to compute the characteristic equation, which is the determinant of the pencil defined by n and m. Let delta the discriminant of this polynomial, which is the resultant of f of its derivative. And what we get is the following. So we can characterize, first step, all the positive geometric configurations of, in this case, a circle and the parabola by the conditions of the signs of the real roots of the roots of the characteristic equation and other parameters. In this case, the other parameters are the a coming from the parabola and delta, which is the radius of the considered circle. So let me just show you an image of what we are doing by using Maple, for example, for these 9 conditions. So the case of having only one intersection point and an inner tangent point, which in this case is equivalent to the characteristic equation to have a triple root smaller than or equal than minus a squared. So let me move to Maple, and in this case, we have the parabola in canonical form, we have the corresponding matrix, we have the circle, but in this case, we write the circle in this way because we are going to consider that this is the matrix. We are going to consider that the circle is passing through 3 points in the parabola. We know that in the complex, we have 4 intersection points, but 3 of them we are going to be denoted in this way. For later use, let's consider the resultant of these 2 conics with respect to y, which is giving us the four, let's say, x coordinates of the intersection points. So in order to connect the coefficients of the circle and the xi's here, just we substitute, we replace the points into the circle equation, and we solve these 3 equations with respect to the di's. And so in this way, even you can see that some symmetries arise because even the numerator here can be easily factorized. The next step, we move to the characteristic equation. But we see that even in this case, we are able to solve this cubic equation in closed form, but also you can see here some squares that are going to be very useful in what follows. In this case, the resultant is this case, but what is more important is that factors in this way. This means that we know that the 4th intersection point between the circle and the parabola is given by this expression. We have the 4 points, and now what we make is just to see what is happening when 3 of them are equal. And so in the first possibility, there are many more, we get it in this case. We have here, you can see the triple root. So we have proved that if we have this geometric configuration, our characteristic equation has a triple root, and you can easily see that this triple root is smaller than minus a squared. So let me move back to the presentation.
12 minutes.
Yeah. Okay, thank you. So we have improved previous results dealing with this configuration. Next step is moving to the conditions on the coefficients, and final step is just inverting the corresponding affine transformation. So you can see here one concrete case where we see what do we get. So we get, for example, in this case, 4 points of intersection if and only if these polynomials verify these conditions, where all the polynomials involved come from coefficients of the considered matrix. So conclusions. So I have tried to see that how closed form solutions try to concentrate at the very end the application of numerical techniques. Typically, these formulae are very important in applications because typically they are used many times. Think about moving objects I was mentioning at the beginning. And the use of Maple for deriving this concrete formula has been extremely useful because we have many possibilities to take into account and many formula to investigate. You can see all these developments just looking for our archive paper. Thank you very much.
Thank you, Laureano. Does anyone have any questions, or if they want to speak out or put them in the chat? All right, if no one else has one, I have one. So I noticed, well, one thing, you managed to significantly reduce the complexity of the conditions to a set of much easier conditions to work with. Have you, in looking at those, managed to determine that, not just using directly quantifier elimination, but there's a way of by hand reducing those even further? Or does it get you as far as you can,
let
as
me
simple
tell
as you're
you,
getting?
yeah, let me tell you that Maple was extremely useful, but there are also many human work on this formula. It's not only
Yes.
Maple producing
Yep.
the formula. There are many other simplifications that help us just to significantly to reduce the complexity of the formula we are producing. So Maple, in some sense, is the first step. But then we need to look for symmetries and many other simplifications. For example, the removing cases that we know that are empty in the case that they will never happen. But this is
Right.
human base, not only Maple.
Right. Yeah. Okay, thank you. If
Thank you.
there are no further questions,
Actually, just one came in
Oh,
from
okay.
one of the speakers. Could you discuss more about how this is used in robotics, as mentioned in your opening remarks, how
Yes,
it would apply?
well, let me give you one concrete example. Think about, but I will use ellipsoids and not conics, but it's quite similar. Think about an arm, and you enclose each part of the arm, let's say an ellipsoid. And then the object you want to move is also enclosed by an ellipsoid, and you want to, during the movement of the arm, you want your ellipsoid never just to cross the object you want to manipulate. So these formula are quite useful just to check, to verify, to guarantee in advance that they will never happen to have an intersection, that to have, let's say, a common interior point. This is the reason why at the beginning of my talk I was using the interference problem for ellipses, because in many cases you are only interested about when the ellipses are really separated by a line. You will never collide.
Yes, and optimizing the kinematics, I guess, as well, right? But it's
Yes,
the
of course.
path,
Yes.
right? And there's one also written in the chat, just passed to me. How much effort is required to extend these from 4 intersections to 5? Has there been any look at that jump?
You were moving to 5, what?
5 intersections.
But 5 intersections for 2 conics is not possible.
Oh, maybe it was a typo. But to extend it to more further intersections, then is this something that could be looked at further, or is 4 really the limit of most of the research?
Now, let's say this method applies just for conics and similarly for quadrics. Let's say that, but only, let's say, degree 2 equations in both cases, for the plane and for the space. But in the case, even in the case of conics, there are no more than 4 intersection points, and this is the reason why this is the limit, we know.
Thank you.
And the case of quadrics is more complicated because you have the intersection is a curve.
That makes sense. Thank you so much.
Okay, thank you, Laureano. I'd like to introduce our next speaker, Bahia C. Lakhal from the University of Science and Technology, Buari Boumadiene. I think I pronounced that correctly. If you could please share your screen, Bahia. Okay, and we can't
Hello,
hear you yet.
everybody.
Oh, there we go. Perfect.
Can you see me?
Yes, we can
Yes.
see your screen and we can hear you. Excellent. Thank you. Please go ahead.
So I am happy to take part to this conference. My name is Bahia C. Lakhal from USTHP University in Algiers. Today I will present a well-known example from general relativity, the advance of perihelion of Mercury, and show how we can use Maple to solve and visualize the equations involved. Okay, so in this presentation, I will derive the orbital equation. by using the Euler-Lagrange equation formulas. And I will show how to solve the corresponding differential equation using Maple software. Then I show how to find numerically the value of the advance of Mercury's perihelion and visualize the orbit numerically. So before starting the topic, it is useful to explain what is the perihelion. For a planet orbiting the sun, the perihelion is the point of closest approach to the sun, as seen in this figure. So, in Newtonian mechanics, the orbit of a planet around the sun is an ellipse that remains fixed in space. However, its observations, in particular for Mercury, show that this elliptical orbit slowly rotates over time. And so Newtonian mechanics cannot explain this phenomenon known as the advance of the perihelion. However, in general relativity, the sun's mass curves the surrounding space-time, and Mercury follows a geodesic within this curved geometry. So we will see later that general relativity can explain the advance of the perihelion of Mercury. As I said, I will use the formalism of Euler-Lagrange to find the orbital equation. We define a quantity 2k, which is a Lagrangian-like quantity, and write the Euler-Lagrange equation by solving the Lagrange equation for the variables t, theta, and phi. We can derive the constants of motion, called the h. The h, which represents the angular momentum per unit mass of the planet, and E, which is associated with the conservation of energy. By substituting these two integrals of motion into our equation, we obtain this following equation, which depends on R and phi. As here is the Schwarzschild radius. Now, to study the shape of the orbit R as a function of phi, it is convenient to introduce a variable u equal 1 over R, and then find a differential equation u of phi. This is our differential equation that we can simplify more to find this equation. This equation represents the relativistic orbital equation for a planet moving in the Schwarzschild geometry. Now we will apply an approximate method to solve the orbital equation by differentiating the equation 17 with respect to phi. We obtain this equation called the relativistic form of Bennett's equation. It differs from the Newtonian version by the presence of the additional term 3 over 2 R as u squared. This term represents the general relativistic correction responsible for the precession of the perihelion. Now, to find the solution U of phi, first we neglect the second term in equation 18. Then this equation reduces to the Newtonian orbital equation. Its solution is simply found. It corresponds to a Keplerian ellipse, where E is the eccentricity of the ellipse. Now, since the Schwarzschild radius RS of the Sun is extremely small compared to the orbital radius of the planet, we expect that the general relativistic corrections to the Newtonian motion are very, very weak. So we expect that in general relativity, the solution of equation 18 is solutions approximately elliptical, but with the subtle precession of the perihelion after each revolution. Okay, so in Newtonian mechanics, the orbit of the planet around the Sun is a closed ellipse, but in general relativity, because of the term of the additional term, we will have an ellipse which is precession of the ellipse. This means that the perihelion advances by a small angle after each orbit. We can solve equation 18 perturbatively by treating the relativistic term as a small correction to the Newtonian solution. I skip the detail of calculation here, and I just give the angular shift of the perihelion per revolution given by 21, where A is the semi-major axis of the orbit, E is the eccentricity, and M is the mass of the central body, here the Sun. Now, if we apply for the planet Mercury, where the parameters A and A are given, we substitute these parameters in 21. We find delta phi equal 43 arc second per century. This value agree very well with the observed anomalous precession of Mercury's perihelion, showing that the confirmation that Einstein's general theory of relativity is successful. Okay, we can solve 18 numerically by using the dissolve command in Maple to obtain the function u phi. Here, it's another alternative to find the delta phi. Delta phi here is given, the value is given by using the formula 21. Now, I will solve numerically the differential equation. And so the goal of the numerical integration is to determine the shape of the orbit, and in particular the position of the perihelion, which corresponds to the minimum value of R, or equivalently to the maximum value of U. To locate the minimum of R, we have to note that at the perihelion, the derivative of R with respect to phi equals 0, or equivalently, the derivative of U with respect to phi equal 0. So in this numerical solution, we can identify the angular position phi equals 0, where this derivative vanishes at the point of closest approach. So the Maple worksheet that I can show here, for example, here for the you see here the value of precision, which is 42.3. This is not degree because the Maple doesn't, I can't write here arc second. It is not possible here. Degrees, we cannot make arc second. So I try to print the result, but I've thrown with an error. Okay, so I return back to my presentation. In the simple Maple worksheet, I followed the following steps. I defined the differential equation 18 for u of phi. I specify the appropriate initial conditions, u of 0 equal u0 for mercury, and the du over d phi at phi equals 0 equals 0, which corresponds to the perihelion. Then I use the dissolve command with the numeric option to integrate the equation over several orbital periods. Then I extract the successive maxima of u phi or minima of r phi to determine the angular shift of the perihelion. Okay, so as I showed you, the delta phi found is approximately equal to the value delta phi 43 arc second per century.
12 minutes.
Okay. These are the numerical results with Maple. Here is the relativistic orbit of Mercury. As you see, it is hard to see the precision because for here the plots of R phi and U phi exhibit small periodic variation. So as a conclusion, using Maple 2018, we have numerically and analytically studied one of the most famous tests of general relativity, the precession of Mercury's perihelion. The computed results are in excellent agreement with both the analytical formula and astronomical observation, which means that general relativity is successful in some domain of physics, of course. Thank you for your attention.
Thank you very much, Bahia. So does anyone have any questions at this point?
I
Anything in
have
the chat?
a comment which I've just put in the chat that this classic problem, very nice talk, by the way. I very much enjoyed the talk by you. It's one of my favorite books is D.F. Lauden's book on elliptic functions, and he shows how to solve this differential equation analytically. I don't know whether DSolve in Maple will produce the answers in terms of Jacobian elliptic functions, because it needs to decide whether certain things are positive or not. And I just don't know. But it might, and it might be worthwhile to pursue that, to compare that to your perturbation solution. But I highly recommend the wonderful book of D.F. Lauden. He's also written a book on general relativity, but I've never read that one. But the book on elliptic functions has this solution. I've also got the solution by perturbation methods in my new book with Nick Fillion, perturbation methods using backward error, which also uses Maple, but that's not published yet. So next year.
I don't have the book you said. If you mind to send me the reference, because in fact, I am teaching Introduction to General Relativity to graduate students, and this presentation will be application for students. It will help them to deal with the computation and physics concepts. And of course, if analytic solution exists, it will be better for me to show it to my students.
I like elliptic functions. Elliptic functions are wonderful, but not everybody knows about them nowadays. So the question of whether it's a better than a numerical solution or not is actually a hard question. But I certainly like them, and I hope you like them too.
I think in for Newtonian Binet's classical Binet equation, we can find the exact solution, but in general relativity, I don't think so.
For this particular one, yes, it's a surprise, but yes,
because of the term this term.
yes.
Okay.
It is a surprise that equation with that extra u squared term can be solved analytically. And it's because you've got a first integral up above it. And that first integral itself can be integrated using elliptic functions. So the description is in D.F. Lauden's book. It's a surprise. People don't think about elliptic functions anymore because they were better known in the 19th century than they are now.
Okay.
I'm delighted to be able to tell you something about elliptic functions. I will send you the reference.
Okay,
I think I have your email.
Thank you very much.
Thank you very much, Bahia. If you could stop sharing, we enjoyed your talk and the discussion. I'd like to introduce our final speaker for the session, Son Ho from Celtic Engineering Incorporated. Son, if you could start sharing your screen, that would be great.
Yes, sir. Let me share my screen.
Perfect.
Okay, I think it's on. Everyone see my screen?
Yeah, we can see it fine. You might want to zoom in a little bit, though, on
Okay.
the presentation. So perfect. I think that's fine.
Okay, so hi everyone. My name is Sean Ho. I'm working for Celtic Engineering in we are headquartered in Florida, and we have an office in Los Angeles area. So we work in the theme park, amusement rides industry, and aerospace. So today I'd like to share with you something related to a project that I'm working on. That so in amusement rides, we very often encounter the kind of pendulum rides, which is very simple. You know, our children play with the swing in front of the house under the tree all the time. But you go to the amusement theme park and you just pay more to get on the ride. Basically, it's a swing. But then because it's huge and it can be a lot of engineering involved in that, so it is a part of the work that we have to look into the dynamics of the system. And we start with something really simple with the pendulum. So I can share with you. Okay, so this is a idealization of a pendulum, right? It comes in many shapes and forms, and but this one is a simple one. So you have an arm and you have a gondola where people sitting on. So you see the gondola down here with the red dot representing the CG, the center of gravity of the gondola. And so the pendulum problem is a classic problem in every textbook, and nothing new about that. However, when you start having another degree of freedom and the system become chaotic, and that's where things get messier. And Newtonian mechanics is great, but when you start having more degree of freedom and you have a full mechanism with multiple parts connect to each other, then it can be cumbersome. It's still doable. So that's where we can use Lagrangian mechanics to deal with that. So I will start with, I will have 3 parts. One is I look at a simple pendulum and establish how I solve it in use Maple to implement the solution and check a few things. And then the second step is to solve the same problem but derive the equation of motion using Lagrangian. And the third is looking into a double pendulum. One is compound, meaning that it is the account for the moment inertia of the link. And the second one is a simple pendulum, which is a mass, a concentrated mass at the end of the arm. So which is this one. So the first link is the gray area here, which is the arm, and the second link is the one with the red dot. So I will share with you. These are the textbook problems. If you have a pendulum with a theta angle, then the equation of motion is theta second derivative plus g/L sine theta. Now we know that for the actual swing, typically in textbook you will solve it with the assumption of small angle approximation first. But in real life, we typically have large angle, which makes this problem nonlinear by nature.
Son, if you
So-
could zoom in a little bit more on this as well,
Oh, I'm
please.
sorry. Yeah, I
Yeah.
just went to.
Thank you.
Okay, let me.
Perfect.
Is
Thank you.
this good
That's-
enough?
I think that's good.
Right. So we I will skip through this one a little bit. Now, this is just simple calculation, the gondola, and then we have, according to the ASTM standard on designing amusement rides, we need to design the gas weight of 300 pounds each. And in this ride, we have 18 seats. So that 18 times 300 plus the empty gondola, we end up with 16,300 pounds. And then to make the system unit consistent, I use foot, pound, and slug. So we assume this pendulum swing ride is having the length of 190 feet. And this is from textbook. So if you do a small angle approximation, the period would be 15.2 or 3 seconds. And then let's assume that the initial angle is 80.7 degree, meaning that you pull the pendulum up to 80.7 degree and you let go. Then you have a pendulum. So based on those, this is because eventually we will have to solve it with a numerical method because it's nonlinear by nature. So we plug in the numbers, and this is the formula. This is the equation. This is the boundary. Initial conditions. And again, from textbook, you can find the exact period using this formula. And it does, it results in 17.4 seconds as period compared to the small angle approximation at 15.3. And so I use the resolve command to solve it. And then let's go look at this one. So the red curve is the angle in radians. The blue curve is angular velocity in radian per second, and the green one is angular acceleration in radian per second squared. So we can verify from here that the period indeed is 17.4 degree. I'm sorry, 17.4 seconds. And the other way we can we can verify that is we find the points that we find the point right here. A period is from here to here, and then velocity equal to 0 means that angle is maximum or minimum. So 1 point, 2 point, 3 point, and I use fsolve to find the 0 point right there, and the distance from this point to this point is actually 17.4 seconds. for this engineering problem, the interest is also on the force, the radial force at the pivot. So going through Newtonian approach, first thing we find the acceleration from that solution. So these are the acceleration. We have the tangential acceleration and we have a centripetal acceleration, and the square root of sum of square of those two is the resultant acceleration. And using that, we can find the centrifugal force based on the acceleration and find the total radial force on the pivot. That would be combined of the component of weight at certain angle and the centrifugal force at the same angle. So this is just an exercise going through the simple pendulum and find out the motion and the radial force. The next step is to do the same thing, but going through Lagrangian mechanics here. And let me zoom it in. So these are again a textbook approach, and the Lagrangian equation can be written in this form, and then the same set of parameters all over again. But the difference here is we start dealing with making the kinetic energy and the potential energy for these. And let me show you, these are just the preparation. But when I consider the simple pendulum, first thing is we write the coordinate system of the points in there. And then in this case, let me go back to this one. When we consider the simple pendulum, we assume that the red dot is on the center line of the gray link. And this is one pendulum, one single pendulum. And assuming that the arm here have no mass and no moment of inertia, just the CG right here at the red dot right here aligning with it. And going through the substitution here, we can, first thing is we write the coordinates, Cartesian coordinates of the points, and then find the kinetic energy and find the potential energy and plug in the Lagrangian equations, and we end up with this. And more math, but these are just standard steps in Lagrangian equations. And at the end, after the math, we end up with this equation, which is exactly the same thing as the equation from Newtonian mechanics. So this exercise is to confirm that the math to derive the motion equation through Lagrangian formulation come up with the same equation as the Newtonian approach. The other interest in here is to find the cable tension at the pivot point, or not cable. I mean, this is a remnant from something else, but the arm radial force at the pivot point. So this one is tricky because on a Lagrangian, purely Lagrangian, we don't have the reaction per se, because we don't go through the force like Newtonian. We just go through the generalized coordinates. So in order to recover that, because it's important for design and engineering of the system, I have another degree of freedom right at the pivot point and write another equation for that. So through that, I get this one out, and we know that this one, even though it's the same as the radial force from the previous exercise through Newtonian, but the last one was from, you have to calculate for the acceleration and calculate the force from there. But this one is just purely math coming from those differential equations. And
minutes.
we repeat. I'm sorry, go ahead.
Sorry, it just said 12 minutes. You're at 12 minutes.
Oh, I'm sorry.
Yeah,
Yes.
just like
Okay. So we go through the same exercise of checking and how to get the numbers out, because that's important. And it come up with the same values. Now I go to the last part of that. When, let me blow it up. Now I'm considering the system with two degree of freedom, which a compound pendulum plus a simple pendulum. Number one is compound one, number two is a simple. And we go through all the math, and now it's getting much more cumbersome. And this is where I appreciate that Maple can help me do this, because it's hard to do this by hand without mistake, at least for me. So we go through all of these and plug in the values. And there's a lot, sorry, that there's a lot of math, but I think everyone can appreciate on those long formulas. And then we solve it and plug in the values. And then this is where we see the angle of the main pendulum still remain the same, but we have ripples in there that we don't see very well. But then when you look at angular velocity, which is blue, we start seeing that the effect of the second degree of freedom. And when you look at acceleration, you see it even more. The green one is the angular acceleration, it's even more. And again, we need to get the radial reaction out of the pivot point for design purpose, because it needed to design the whole support structure on top. And then we start seeing these. And the last step is we consider the initial condition of the second degree of freedom, which is the gondola, the initial angle of the gondola. And you can see that if you start at 0 degree, meaning that it aligning with the arm, it's less. But when you start increasing the initial angle, it's getting a lot of variation around that. And then the offset angle between those two will give you this. And acceleration, angular velocity will show the same trend, that you have a lot of variations around the sine wave. And that will affect the reaction force on the pivot. And that's important because we use that to design the structure. And then down here, it's just my exercise of finding the peak value, because right now I think Maple may be able to improve that, because when you have a lot of up and downs, it's hard to pinpoint the maximum point. So I had to look at that closely, and I narrow the range that I do the F-solve. And then through all the exercise, I plot the peak tension versus the initial offset angle, and then I compare that to the rigid body dynamics model from ANSYS. ANSYS is it's a FEA software, and it have a module for rigid body dynamics, and they actually sitting on top of each other. So this is kind of a independent verification for ANSYS, or ANSYS do this one. And that this is what I want to share with you.
Thank you very much, Sun.
Thank you.
Okay, do we have any questions? If anybody wants to take themselves off mute.
There's one comment in the chat so far. In general, there's another approach to working, which is to assign the values to variables up and ahead, but not to evaluate them, and instead to assign them as a parameter set and evaluate at the end. That way, you can always change the parameters in a more clean way along as you go. So there's just a comment from another person working with physics and mathematical modeling.
Yeah, understood. I appreciate the input.
Yeah, and I'm going to add to that a little bit, in that not only that, you don't even need to assign them before you call dsolve. You can actually leave them as parameters and tell dsolve that these are open parameters, and then set them at the time that you want to compute the solution or look at a plot.
Correct. Yes. One reason is yes, I do appreciate that. One thing I counting on is because I have the three. So if I treat this worksheet as a tool, I just replace the parameter. Let's say I assign at the top of the thing.
Yes.
Right here. This is where I find it. So I can replace right here and press the the run button here, and I generate everything all over again. So
And it takes care of it all. Yeah.
Yeah, so it's kind of convenient for me to do that instead of going through the middle of the worksheet and try to change some numbers there. I think that's why I did what I did.
Okay. Yeah, it makes sense. Yeah.
One other question that came in was, how does this model compare to the data from an operating system, such as actually an actual real-life gondola? Is there other friction and other effects that you'd have to consider?
Oh, yes. So this one is just to demonstrate how I use Maple to implement the process. But yes, the real gondola actually is much more complicated than this one. For example, we have to consider the wind, the friction, when the gondola moving through still air, not considering operational wind just yet. We already have some wind drag, right? Air drag on it, on the arm and on the gondola itself, and then because it's up high in the air, so we have high wind load that we calculate through ASCE 7 per code for the building code, and so that, and also we have multiple other kind of conditions that we consider for both strength design, fatigue design, but that too deep into the engineering part. Right now, I just want to limit this one as a very fundamental, looking at the Pendulum system, and just the consideration of the gondola with a pin joint right here already make it more complicated, but at least we have a mean to estimate the effect of those. And right now, what I have in this presentation is the effect of the angle, the initial angle from this line to this line. It already affects that, and we do know that. We just need a way to estimate that. But we do need that if we have 2 degree of freedom right here, we have a chaotic system, and that can be very messy. But right now, what I'm deriving at is I can estimate how much the chaotic affecting the radial force at the pivot point. And that's the key value I need to design the structure up here to support the whole system. And there's so much more into this one, but yes, there's so much more phenomena to consider, which I'm not including in this presentation.
It certainly gets you to the right order of magnitude for the structure, for the structural support. Yeah, thank you.
Yeah, thank you.
Thank you, Son. So that brings us to the end of the first part of the applications and research contributed talks.